Now I'm going to explain the basic working principle behind eddy current proximity probes. The probe consists of a coil which is shaped like a flat disc, and it's inside the tip of the probe. The tip is attached to the metallic body, which is usually threaded, so it can be attached to some kind of bracket or support using a couple of nuts. That coil inside the tip is excited by an electrical sinusoidal signal called the carrier signal, and which is an electrical signal of high frequency in the order of megahertz. When that carrier signal goes through the coil emits an electromagnetic field in front of the sensor. And then when a target material crosses that electromagnetic field, an electrical current will be induced on the surface of the target material. This electrical current is called eddy current. The strength of that eddy current will depend on how close the target material is to the tip of the probe and will impact the impedance of the coil itself. So the closer will be the target material, the stronger will be the eddy current on its surface, and the higher will be the impedance of the coil. To measure changes on the impedance of the coil, we can just measure the amplitude of the carrier signal. So if the target is closer to the tip of the probe, the amplitude of the carrier signal will go down. And this amplitude is represented in this animation as a blue line. This is the static position of the target. Then, if that target starts to vibrate, it starts to move fast, the amplitude of the carrier signal is going to change accordingly. It's going to change fast. And this is what you see here represented as the orange signal. So we have both the AC component and the DC component on the amplitude, on the modulated amplitude of that carrier signal. It's important to take into account that the performance of the system will change depending on the conductivity properties of the target material. So steel or aluminum or other alloys have different conductivity properties that will produce a different response of the system. For example, if we talk about wood or plastic or ceramic, since they do not, they don't conduct electricity, they will be not seen by the sensor. The standard target material is 4140 type steel, and eddy current probes calibrated from factory are by default calibrated for this material. But you can make a special request, and the system can be calibrated for other materials that you can provide a sample or request some other standard materials. And by the way, this standard steel is not something specific to vibrometer, but it's the standard de facto in industry, which is used by other manufacturers. Within a proximity measurement chain, the signal conditioner generates this excitation carrier frequency and also demodulates the signal returned by the probe to provide a voltage or current output that is going to be proportional to the gap. The most common choice is to use a proportional voltage output, but later in this lesson, we will discuss a unique feature of vibrometer proximity systems, a key differentiator, which is the option to provide a proportional current output that can be selected instead of voltage if that's required. It's important to remember that these are instantaneous voltage or current outputs and not static or quasi-static signals, such as from 4 to 20 milliamp process transmitters. We can therefore obtain a true instantaneous waveform output from a proximity transducer system, making it useful not only for shaft position, but as well for shaft vibration, for phase reference, for shaft rotating speed, and for many other measurements. Another important aspect to understand of proximity probe measurements is that the gap can change due to motion of the probe itself, motion of the target or motion of both in parallel. Since the probe senses only the relative change between itself and the target, it's sometimes called a shaft relative probe. Generally, for vibration measurements, we assume that the motion of the shaft is much larger than the motion of the casing to which the probe is attached. But this is not always the case with highly compliant machines or with turbomachinery. And in such cases, both vibrations have to be measured and then summed vectorially into a composite measurement result. In a later lesson, we will show how the relative measurement made by a proximity probe can be adjusted using a separate casing vibration measurement to provide a so-called shaft absolute measurement. For now, however, it's enough to note that a change in the gap can occur due to movement of the probe, usually affixed or attached to the machine casing, movement of the target, which is going to be usually the shaft, or movement of both of them in parallel. The probe system fundamentally converts a change in the physical gap to a change in electrical output, either voltage or current. Here we assume a voltage output, as you can see in the vertical axis of the graph. The horizontal axis shows the gap in mils or thousandths of an inch. Outside of North America, it is typical for the horizontal axis to be in micrometers, sometimes called microns, but we will use mils in this training because the math will be easier to do in your head than if we used metric units and a typical corresponding scale factor of 7.87 millivolt per micrometer. The scale factor simply refers to the relationship between gap and voltage. It's shown by the yellow line on the graph. If we want to convert gap to voltage, we simply select a particular gap, then extend vertically until we hit the yellow line, and then proceed horizontally to the corresponding voltage. The most common scale factor is 200 millivolt per mil. This is equivalent to 7.87 millivolt per micrometer. However, when doing computations in your head, and for the examples in this lesson, 200 millivolt per mil is easier to work with than 7.87 millivolt per micrometer. And this is the only reason we have chosen to use imperial units instead of metric units. But in practice, you will need to be able to work in either system of measurement. And depending on where your customer is located, they may be using imperial units or metric units. The scale factor we have chosen for this example is 200 millivolt per mil, since it's the most common in practice. To visualize how this works, let's first employ a triangle. The slope of our yellow line is the scale factor. For a given horizontal distance on the graph, the scale factor implies a given change in the vertical direction. You can think of this as the slope equals rise over run. The rise is 200 millivolt and the run is 1 mil. In other words, for every 1 mil change in the gap, the voltage changes by 200 millivolts. The important takeaway here is that the scale factor is simply the slope of output, millivolts, versus the input, the gap in mils. If we were to use the metric system and change our horizontal axis to micrometers, the scale factor would become 7.87 millivolts per micrometer. And now, let's use this concept to convert a changing gap to a changing voltage. Here we have shown a 20 mil change in gap. At 20 mils of absolute gap, the voltage is minus 4 volts. And at 40 mils of absolute gap, our voltage is minus 8 volts. The 20 mil change in gap, therefore, corresponds to a 4 volt change in output. Now we show an 80 mil change in gap. At 10 mils of absolute gap, the voltage is minus 2 volts. And at 90 mils of absolute gap, our voltage is minus 18 volts. An 80 mil change in gap, therefore, corresponds to a 16 volt change in output. Probe systems exhibit a linear range as shown by the shaded area of the yellow line. Inside the linear range, the probe system delivers a consistent scale factor that is accurate within factory specifications, regardless of where we are along the line. In this example, the scale factor is 200 millivolts per mil, and the linear range stands from 10 mils to 90 mils. Different probe systems will exhibit different scale factors and different linear ranges. To give you an example, while we have depicted the scale factor and linear range for a typical probe system with an 8 millimeter diameter tip, like our TQ902, the scale factor and range for a probe system with a 13 millimeter diameter tip, such as our TQ922, will be different. In the case of the TQ922, the scale factor can be ordered as 100 millivolts per mil, and the linear range will be twice as large at 160 mils. Other probe systems with even larger tip diameters will give even larger linear ranges, but correspondingly smaller scale factors. Such probes are used in applications such as differential expansion, where gaps greater than 4 millimeters or 160 mils are required. For example, the TQ403 has a tip diameter of 18 millimeters and a linear range of 12 millimeters or 470 mils. Outside the linear range, the probe system will not deliver the correct scale factor and therefore should not be used for machinery measurements. If a greater distance or gap must be measured, a probe system with a greater linear range must be selected. As mentioned previously, our vibrometer portfolio contains probes with various tip diameters and linear ranges. Because a larger tip diameter allows a larger coil diameter to be encapsulated inside, this means that larger tip diameters and their corresponding larger encapsulated coils correspond to longer linear ranges. So, for example, a probe with an 8 millimeter tip diameter will always have a smaller linear range than a probe with 25 millimeter tip diameter. OK limits are basically thresholds set in the vibration monitor that coincide with the upper and lower extremes of the linear range. This allows the monitoring system to enunciate when the probe system is delivering a value that is outside of its linear range. For example, a shorted wire to ground will usually result to a 0 volt output and cause the monitor to enter a not OK condition. At the other extreme, a value exceeding minus 18 volt is usually also flagged as not OK, and might mean that the signal and power wires have been shorted. The OK limits are really a valuable diagnostic tool when troubleshooting the measurement chain. They also help to prevent false trips of the machine by suppressing other alarming functions if the transducer is not okay. Now let me give you a useful convention to memorize for signal polarity. The motion toward the probe tip results in a positive going voltage. Although all the voltages are negative, a positive going voltage means that it is less negative than the prior voltage. You can also think of it this way. As the magnitude of the gap gets smaller, the magnitude of the voltage also gets smaller. To illustrate this, let's look at the voltage when the gap is 60 mils. Notice that the output voltage at this gap is minus 12 volts. Now, let's decrease the gap to 40 mils. And notice that the voltage rings as well, and now is minus 8 volts. So, smaller gap results in smaller voltage amplitude. Before we leave this topic, I want to make one additional observation. You may wonder why the response of the transducer becomes nonlinear outside of the linear range. If you remember, the electromagnetic field emitted from the probe that we illustrated previously, you can easily imagine that if the probe tip is too close to the target, the maximum field is absorbed. So moving the target closer to the probe will not result in any additional field strength being absorbed. This is illustrated by the horizontal part of the yellow line below 10 mils. Placing a target closer than about 10 mils will not result in any change in voltage. It simply levels off at slightly below 2 volts. At the other end of the linear range, above 90 mils of gap, an opposite situation occurs. Now the probe is too far away from the target that a change in gap does not give proportionate change in electromagnetic field and corresponding eddy currents. Eventually, the probe is going to be so far from the target that it can no longer induce any eddy currents at all. And the output does not change. The output eventually saturates somewhere beyond minus 21 volts. Trying to operate in either of these upper or lower regions beyond the okay limits, it's really undesirable because the relationship between the gap voltage no longer respects the published scale factor. It's important also to note that the okay limits are established in the monitor. The transducer itself does not self-detect when it's operating outside of this linear range. It simply provides a voltage output based on the observed gap that it detects. To help reinforce your understanding of probe gap and voltage output, this animation will help. We start with the probe observing a target where the target is placed 20 mils from the face of the probe. As can be seen by the solid blue line, this gap results in an output of minus 4 volts. Now let's increase the gap to 40 mils. And notice that the voltage becomes larger. It is now minus 8 volts. We will now increase the gap one more time, this time to 60 mils. And notice that the voltage again becomes larger. It is now minus 12 volts. Changing the gap to a static position, as I have shown, is known as static gap change and can be accomplished by using a dial micrometer and a target plate. In fact, this is how a probe system calibration is often verified in the field. You can click the video to watch an example of a dial micrometer and a probe fixture used for verifying correct operation with changes in status. Now let's discuss another type of changing gap. This type of gap change is not static. Instead, it's dynamic and it's caused by the vibration of the target, which is going to be usually a shaft. We can simulate vibration by either attaching a target to a shaker table and then affixing a probe above the target, or by using a wedge-shaped rotating plate known as a wobulator. With the probe in the center of a wobulator's rotating plate, the probe will observe no vibration at all. However, as the probe is moved toward the outer diameter of the plate, the wedge shape results in a greater changing gap as the plate rotates, and the short end of the wedge passes under the probe, followed half a rotation later by the long end of the wedge. Both the wobulator and the shaker table methods are commonly used in the field. Nevertheless, an advantage of the shaker table, however, is that it can be used for checking more than just proximity probes. Instead of attaching a plate to the vibrating part of the shaker table, sensors such as velocity coils and accelerometers can be attached and then shaken at known amplitudes and frequencies. With a proximity probe, the target vibrates, while with a seismic transducer, the transducer itself vibrates. We will talk more about seismic transducers in the next lesson. Let's now illustrate the effect of a dynamically changing gap by introducing the vibration sinusoid in blue. This represents a shaft vibrating sinusoidally about some center position, which is its average gap. In this example, the amplitude of the vibration is 20 mils, as can be seen by observing the grid lines on the graph. The sinusoidal oscillation goes as low as 40 mils of gap and then up to a maximum of 60 mils of gap, and then back again. This vibration is centered about 50 mils of gap, and this average gap would be observed on a voltmeter as minus 10 volts DC. This sinusoidal change in physical gap will result in an output voltage that is also a sinusoid, as you can see here in green color. When the gap decreases to minus 40 mils, the sinusoid reaches its minimum output of minus 8 volts. Then the sinusoid heads towards its other extreme at 60 mils of gap and minus 12 volts at the output. It then swings in the other direction, etc. The sinusoidal input, the changing gap, results in a sinusoidal replica at the output, which is a changing voltage. One is changing gap, the other is changing voltage. A real probe will exhibit a signal with both AC and DC components. The AC component will reflect the changing gap, while the DC component will reflect the average gap. Physically, the DC component represents the average distance of the shaft from the probe. The AC component represents how the shaft oscillates about its average position as it vibrates. The amplitude of this AC component should not be confused with the DC gap voltage. We could have 20 mils of vibration centered about 50 mils of gap, or we could have 20 mils of vibration centered about 40 mils of gap. Each could give an identical AC signal of 4 volts peak to peak. However, one would be centered about minus 8 volts, while the other would be centered about minus 10 volts. To help further reinforce the concept of dynamically changing gap, I propose you watch this video, which shows a shaker table providing sinusoidal vibration of a target plate while being observed by a stationary probe. As the amplitude and the frequency of the vibration changes, the amplitude and frequency of the voltage output from the probe system also changes identically. Let's have a look now at the complete probe system. As you can see on this drawing, the probe system consists of 3 basic components: the probe and its integral cable, the extension cable, and the signal conditioner. The signal conditioner has 3 fundamental tasks. First, to excite the probe coil so that it emits an electromagnetic field, then to demodulate the return signal from the probe, and third, to linearize the signal so that a consistent gap versus output relationship is maintained across the linear range. You can think of the signal conditioner, the probe, and the extension cable as forming a tuned circuit consisting of resistance, inductance, and capacitance. R, L, and C must be precise values for the tuning of a given signal conditioner. And these values are a function of cable length. So a signal conditioner must be matched to not only the probe family, such as the 900 series probes, but also to the total length of the probe's integral cable plus its extension cable. Signal conditioners are available in 1 meter, 5 meter, and 10 meter tuned lengths. The combined probe integral cable and extension cable lengths are then chosen to match that of the signal conditioner. We refer to this as the total system length, or TSL. To give you an example, if a probe has a 1 meter cable length and an extension cable has a 4 meter length, then a signal conditioner tuned for 5 meters should be selected. 1 plus 4 equals 5. However, if a probe with a 2 meter integral cable was used instead, the probe and cable would now become 6 meters in length and would not match the signal condition. 2 plus 4 equals 6, but the signal conditioner is for a 5 meter system. In some cases, an extension cable would not be used at all. For example, a probe with a 1 meter integral cable could be connected directly to a signal conditioner which is tuned for 1 meter, without use of an extension cable. The criteria is that the total length of cable, regardless of whether it exists entirely at the probe or as a combination of the probe and the extension cable, must always match the tuned length of the signal conditioner. It is also worth pointing out that the 1 meter tuning length is only available in the newer IQS 900 signal conditioner, which can be used with both 400 series and 900 series of 8mm or 5mm probes. The 1 meter tuning length is not available in the older IQS 450 signal conditioner, and instead only in the newer IQS 900. Later in this lesson, we will discuss the compatibility of probe, cable, and signal conditioner model numbers. So both total system length consideration and model number compatibility must be maintained through the system. Not all 4-meter extension cables, for example, will work with all 1-meter probes and 5-meter signal conditioners. A compatibility table is provided later in this lesson to help you in this regard.